The wave function is everywhere in quantum mechanics. It is the key that unlocks a world where particles can affect each other instantaneously, where particles can jump through walls, and where all events are random. All of this is governed by the wave function, and in this video I want to get straight to the point and explain exactly what the wave function is. Let's get into it. Now, to understand the wave function, I'm going to introduce the double slit experiment. The setup is very simple. You have a device that fires electrons. Then you have a screen with two slits in it. Then you have a screen that detects when an electron hits it. Now, to run the experiment, you fire electrons at the screen, and you see where the electrons end up. But what you find is not what you'd expect. You would expect to find two bands of electrons corresponding to the two slits in the screen, but that's not what we find. Instead, we find what we call an interference pattern. An interference pattern is typically created when two waves interfere with each other. Some parts add up, while other parts cancel out. You can also create the interference pattern by running a wave through the double slit experiment. The two slits create two waves, and those two waves interfere to create the interference pattern. This means that electrons, which are particles, have wave-like properties. And so this needs an explanation. Now, to be clear, we still get the interference pattern, even if we run the electrons one by one through the slits. This means that the reason is not electrons interacting with each other. The first thing we can try doing is putting a detector behind the double slits. That way we can figure out which slit the electron went through, and hence its path. But when we do that, we get the original result we were expecting, with the two bands of electrons. The interference is destroyed. This is called the measurement problem. But from this experiment, we can conclude that we cannot detect the path of the electron. Scientists wanted to figure out a way to explain the electron's behavior. Albert Einstein figured out that light, which was thought of as a wave, behaved as a particle. And scientist Louis de Broglie figured out how to find the wavelength of a matter particle, like the electron, which is the equation lambda equals Planck's constant over momentum, with lambda being the wavelength of the particle. Then came along Edwin Schrödinger, who tried to find a way to explain this wave-like property. He devised the Schrödinger equation, and the result of the Schrödinger equation was the wave function. Now, a typical wave function would look like this. Edwin Schrödinger thought that the wave function represented how the charge, technically the charge density of the particle, was spread out over space. Then, when you measured the particle, the charge would collapse back into the electron. But this was wrong. It took another scientist, Max Born, to figure out that the square of the wave function represented the probability of finding the particle at a specific position. This was called the Born rule. Now, before I continue and explain how all this works and how it applies to the double slit experiment, I must point out that the wave function represents different things in different interpretations of quantum mechanics. None of them have been proven, but the most common one is the Copenhagen interpretation. This is the one we'll be referring to today. Because of the particle's wave-like properties, it doesn't have a definite position, so we can only assign a probability to finding the particle at a given location. Before we measure the particle, we say it's in the superposition of states. This means that the particle is in every possible state of the wave function, all at the same time. In this state, they don't have a definite position, just like a wave which is spread out through space. Then, when you measure the particle, the wave function collapses back into one point, where we see the electron. The probability for the wave function to collapse into a specific position is given by the amplitude of the wave function at that position. The higher the amplitude, the higher the probability is to find the particle there. And to be clear, this randomness isn't caused by the lack of information, like a coin flip, where technically, given the right information, we could figure out if it was heads or tails. This is caused by the inherent wave-like properties of the particle, which cause it to be random. Now, to put this into more perspective, let's go back to the double slit experiment. If we were to find the wave function, we would solve the Schrödinger equation. This would give us a wave function that looks like this. Notice how the areas with higher amplitudes correspond to more particles on the screen. This is because those areas had a higher probability. on the wave function and thus had more particles in real life. When you run the electrons through the double slit experiment, they become in a superposition of states. The electron goes through both slits and interacts with itself, creating the interference pattern. Then when it hits the screen, we make a measurement, and the superposition collapses back into an electron. The wave function can be represented in several ways. It can be represented in 2D, 3D, or even other ways. For example, in Richard Feynman's QED, every possible state of the particle is represented as an arrow, and the sum of those arrows is the wave function. The Schrödinger equation can be used to find the wave function of other properties of the particle, like its momentum, energy, or spin. It works the exact same way. You solve the Schrödinger equation, and then you put that property on the x-axis. Then you're good to go. And with that, you should have all the basics of the wave function. If you like this video, click right here to subscribe to my channel. And if you want to see more content like this, click here or here to view some of my other videos. That's it for today. I'm Zaid, and I'll see you next time on The Universe with Physics.